are on optimizations and we are on boxes. There's a lot of different box problems. So here's one. A box with a square base and an open top, so there's no top to it, has a volume of 16,000 cubic centimeters. Find the dimensions of the box, right? Length, width, and height, that would use the least amount of material. So you really have to work on some of these questions. In this kind of question anyway, I would start by trying to draw what the heck it looks like. So I'm going to imagine that I have a square base. If you're a square base, wouldn't you call X and X? Wouldn't you say they were both the same? So I'm calling that X. So the length of my box is X and the width of my box is X. Yeah, it's not bad. Would you agree that's sort of a kind of like what the box might look like? Now, I don't know that distance either, so I'm going to call that right now Y. So that's going to be the height. Are you comfortable about that's what the box looks like? And since it's a square based X and X and an unknown height, I'm going to call Y. So far, so good. So when I'm finished, won't I say it's 10 by 10 by 16, you know, whatever the answer happens to be, right? That's what we're going to finish with. Now, it doesn't have a lid, which is actually quite important. If it did have a lid, wouldn't this probably end up being a cube? You could almost guess the answer, right? If it had a lid, it would look like a cube. But since it doesn't have a lid, that does change the storyline. Remember the last fence we did where there was a river on one side? Didn't you end up with a rectangle twice as wide as it, or twice as long as it was wide? So I do know something like that is likely to happen. Well, the thing that we're being asked to find here is the least amount of material. So they're talking about square footage, right? Now, if I look at this shape, I'm going to call the thing S, right, for square footage, surface area. Isn't this box made out of a bottom, right, a square, this bit here? And isn't the area of the floor X squared? And isn't it also made up of 4 vertical sides? And each side has an area of X times X. Are you happy about the total surface of this shape, the material, is an X squared, the bottom, plus 4 rectangles, 4xy. Are you comfortable where I got that? Right. The floor and 1, 2, 3, 4 sides, right? 4 rectangles. Each rectangle, X times Y. Now, this is the guy that we are going to try and minimize, optimization function, right? That's the fella. And of course, it's not uncommon, as you've noticed from yesterday, that doesn't this function, at least right now, have X's and Y's in it? But don't I only want X's in it? So I'm now going to go back and read this piece. The volume of this thing is 16,000. So you're telling me that the volume is 16,000 cubic centimeters. Won't the volume of this box be length times width times height, right? Length times width times height, which is X times Y is 16,000. So X squared Y is 16,000. If you use this relationship, this expression here, what would I do to find Y then? How would I get from here to here?
Both sides by X squared.
Okay. Are you comfortable with what happened there? Now, this function can now be written with just X's. It's X squared plus 4X, that guy. And now I'm going to try and tidy it up a little bit. 4 times 16 gives you 64,000. That X partially cancels out one of them and you get that. Are you comfortable with these two multiplied and cancelled down gets me that fraction? Right, so what we have now is the function that we're trying to optimize. And when you get to this function, this optimization function is its name, all you need to do is find its derivative and then go looking for critical numbers. And the critical numbers are going to be the place where the answer lives. Now, if I'm going to differentiate this guy, I'm going to have to rewrite it slightly different. I'm going to have to call it 64,000 x to -1. And that's because to differentiate isn't this much easier than trying to differentiate that. So let's see what the derivative looks like. 2x multiplied by the power and reduce the power by 1. And then still points. We're almost finished. We've got our optimization function. We've now differentiated our optimization function. We are after, when is this derivative 0? Or when is it undefined? It's undefined at 0. But if you make x 0, won't that box disappear? So I'm not even going to look at the undefined. I am going to, however, try and solve algebraically when this guy is equal to 0. And this thing is doable. Even if the answer is downright ugly, it's still doable. So here goes. What should I do to both sides to get closer to solving this equation for x?
Add 64,000 over x squared.
I like your thinking. Why did that's the right thing to do? Why do you think that's a good idea?
So that you can cross multiply.
Exactly. So I'm going to have 2x cubed is 64,000. And then if I divide both sides by 2, I get that. And then not square root, but can't I find the cube root of both sides? Are we good with that? Now, I know that the cube root of 32,000 isn't pretty. If you want to simplify it a little bit, you can. It's the cube root of 32 times 1,000. So that becomes 10 times the cube root of 32. And that becomes 10 times the cube root of 8 times 4. And the cube root of 8 is 2, so you get 20 cube root of 4. If you really, really were stuck, you could do that. But I'm happy with that answer. If you got that, you get that. Because can you imagine sometimes the numbers are just not going to come out pretty, right? You know, you might get the cube root of 18 the next time, right? Or 4th root of 92, you know, numbers that are not going to anywhere obvious. So if you get to there, that's good. If you want to know what it looks like, if you make it a little bit prettier, that's it. But this is totally okay. So we are being asked to find the sides of the bases, which is just a fancy way of saying the length and the width. And so that's going to be the cube root of 32,000. And then the height. Now, in my picture, the height was called y. So the sides of bases were called x. In my case, the height was called y. And y is going to be 16,000 over the cube root of 32,000. And don't worry about style points, just let it you know, let it slide. The only time I would worry about making this pretty is if you got really lucky and it was actually a whole number, right? Like the cube root of 8 would be 2, right? And you can check that on your calculator by simply just taking, well, let's take one I know that is, suppose it was the cube root of 8,000, right? So you go 8,000 to the power of 1/3. Now, do you see how that's a nice number? So I would have called it 20 if that had happened, right? But if I tried the cube root of 32,000, and the cube root is just a 1/3 power, you see it's just a ridiculous decimal, so I'm not going to bother. So it's okay to leave your answer like that. Right, cube roots, fourth roots, and horrible. Square roots you can deal with, right? But cube roots are not so obvious. There's my two answers. Any questions? Right, you're going to have a very similar question, but with different volumes, I'm sure. So let's turn that question on its head. Suppose you have the same box as before, but it was made from 30,000 square centimeters of material. And you want to get the largest volume. So got that box, X, X, and Y. Same setup as before. The length will be X, the width will be X, and the height will be Y. We're being asked to maximize the volume. So our optimization function is X squared Y. The total surface area is the same, guys, it was a few moments ago. It's that, but we're told that that is equal to 30,000. And this is the guy that's now going to be used to find Y. So let's go hunting for solving for Y. What could I do to both sides to get closer to being Y equals?
Subtract X squared.
Okay. Sounds like a good plan. What should I do next?
By 4x.
You agree it's a very ugly looking answer, but it is what Y is. So I'll go back now to my optimization function, which is the volume, and it's X squared Y. And I'm going to do X squared times 30,000, take away X squared over 4x. Are we good? Right, let's see if I can make that pretty. And would you agree that you can cancel an X with one of these? And that 4 would probably look better up here. So are we okay with this becomes that? Right. Now I'm going to use a calculator on this. If you take 30,000 and you find a quarter of it, it's 70. I put too many zeros, I did. If you take 30, 1, 2, 3, and you find a quarter of it, you get 7,500 x's. Take away 1/4 x cubed. Do you get that? Are you happy with it? That becomes this. Right. Not the worst looking function in the world, right? That's our optimization function. So I'm going to find its derivative, 7,500, take away 3/4 x squared. And now all I need to do is find its critical number. Find out where the derivative, this thing, is 0. And that's going to be the best shape for the story. So I'm going to put in equals 0. Again, exact values are expected here, so we aren't allowed to, just put it into decimals and find out the number. We have to solve it. What could I do to both sides to solve for x here?
Add 3/4 x squared.
Okay, what do I do next?
Multiply by 4/3.
Oh, great. Divide both sides by 3/4, which is the same as multiplying by 4/3. So 7,500 times 4 divided by 3. And wow, would you look at that? Sometimes you get lucky and the numbers come out nice. Would you agree the next stage is to take the square root of both sides? And that ends up being 100. Technically speaking, is it the answer plus or negative 100? But in the context of this question, would you agree negative doesn't make sense? Well, we should be able to put in all the dimensions. Well, the length of this box that gives you the best volume is x. So that's going to be, what are the units? Centimeters? Yeah, 100 centimeters. The width, which is also x, is also 100 centimeters. And the height, that's a little bit messy, but the height is called y, and y is this thing. 30,000 take away x squared all over 4x. So that's going to be 30,000 take away 100 squared over 400. Let's see what that looks like. On the top, 30, 1, 2, 3, take away 100 squared, divided by 400, and the answer is 50. I'm going to put it in that little picture I've got, even though the picture's not to scale. You're going to get the biggest volume when you make these two guys 100 and you make this guy 50. Right, so it's not a cube. Would you agree it's half the height as it is in the width?
Can you scoot your paper up a little bit?
There we go. So 100 by 100 by 50. Oh, and I just realized they didn't ask us to get them, but we need to find them anyway. They asked us for what the volume would be. Well, since I've got all the numbers in front of me, I should be able to get the volume. The volume is 100 times 100 times 50. So the biggest volume you could get out would be 500,000 cubic centimeters. Are we comfortable with this box? Did you notice, although the two questions we done today had very similar features, right? They were both square base boxes without lids. Wasn't there quite a big difference in the math and the equations, and the details were a little bit different in each case at least? So okay to move now? Are we good with that one? Okay. Now I'm not going to do the next one in total. I'm just going to start it, but not finish it. So we have got yet another box and it's a rectangular box without a lid, is to have a volume of 10 cubic meters. Okay, so its volume is going to have to be 10 cubic meters. That's fine. It has a different shape. It's not square based. It's twice as long, right, as it is wide. And they're using the letter W instead of X, which is fine. You can use any letter of the alphabet you like. I just like X. We've got this guy, goes like that, goes like that, goes like that. Okay, that's not bad, right? That's what the box looks like. The length of the base is twice the height. Okay, now this particular box doesn't have a lid. That's good, right? And what do we know now? The cost of the base is $15 per square meter. And the cost of the sides, well, they're only $9 per meter. So we want to make a box that will hold 10 cubic meters, right? The base is going to cost me $15 a meter. The four sides are going to cost me $9 a meter. And we need to find a function that tells us the total cost. So the function CW is the total cost. Now, the way I see that, isn't it the cost of the base plus the cost of the four sides? Now, the base has an area of, almost forgot. Before I get too far onto this, don't we need this guy here, height? What letter of the alphabet do you want for the height? If they're calling this W and calling this twice as wide, 2W, what are you going to call that guy? You could call it any letter of the alphabet you like, but what one do you want?
Okay.
Okay. I was going to pick H for height because I have no imagination, but K will work. Now, the base then has an area of 2W times W, so it has an area of that, but it's going to cost me $15 per square meter. So won't that be 15 times its area? Are you happy with what I did there? That's the area of the base times $15. Now, there are four sides. Let's figure out what the total area of the four sides are, because they're not the same. For instance, see this side here? Isn't its area 2W times K? Won't the other side be 2W times K? But what about this front side here? Wouldn't this be a little bit smaller? Wouldn't it only be W times K? And the one on the other side is W times K. So when you add that up, 2, 4, 5, 6, there are 6 WK. And this, I don't need that anymore. But they cost $9 each, right? So $9 for every square foot of this. So I now have 30 W squared plus 54 WK. So the cost in terms of W is this guy. And there's a guy, K, that needs to be converted into a W. Great. That K has to be W like everyone else. Now, I know the volume is that. The volume this time is 2W times W times K. So I know 10 is equal to 2W squared K. If I divide both sides by 2W squared, I get K. And if I tidy that up a little bit, K ends up being 5 over W squared. So the cost function is 30w squared plus 54w times k. And now we are about finished. That's 270 over w. Our goal is to find the optimization function. Can you see in this question that it ends up being 30w squared plus, that's 54, so it's 270, right? 270 over w, right? You differentiate that guy and find out when he's 0, and that's you've got the box. While you're finishing that one off. Question 15 has a picture with a frame. The picture goes in the middle, just this guy here. And the frame is 9 inches top and bottom, and it's 6 inches side to side. The area of this picture, right? The area of the frame inside, just this bit here, right, has to be 864, weird number, square centimeters. And we have to find the dimensions of the entire poster with the smallest area. Now that is a puzzle, right? This shaded thing has that area. The poster has to be 6 units either side and an extra 9. So the entire poster is this. And we want to minimize that, right? We want to have a picture with that area inside it and have these spacings around the outside. And we want this total thing to be the smallest area. Well, I've got to start somewhere, so I'm going to start by finding out that guy there, and I'm going to call it X, and I'm going to call this guy Y. Now, the guy that we are looking for is the area of the entire poster. The poster is made up of, right, its length times its width, okay? If I make this unit X and I make this unit Y, let's see if we can figure out how to find the length and width using these. If that distance from here to here is X, what will the total length of this poster be?
X plus 12.
Are you all happy about X plus 12? Right, X and then add 6 either side. Does that make sense? 6, 6 and X. Right, if you go this side then, if that's Y, won't you add a 9 top and bottom? And so you will get Y plus 18. Okay, so this is the optimization function. I'm now going to multiply it by FOIL, so it's going to be XY plus 18X plus 12Y plus a really big number, because 12 times 18 is a really big number. And I'm looking at 216. And I might as well call this guy A then. That is the optimization function, but it has a y in it. And we know that the y's have to be changed into x's, right? I like x's and y's. So is there any piece of information that I could use here that would allow me to find y in terms of x? Did they tell me something that would let me be able to do that?
Well, you already know the area is 864 centimeters squared.
So let's use it then. Isn't the area of this guy xy, and it's 864, agreed? Right, x times y, that guy. And so if you divide both sides by x, don't we get our y guy? Y is in terms of x. So I'll return here, and it's now going to be x times 864 over x plus 18x plus 12, 864 over x plus 216. They cancel and you get 864. You get an 18x. That's a ridiculously ugly number. 12 times 864. So you're going to get 10,368 over x plus another 216. And those can combine, so I might as well do it. 864 plus another 216. We get 1,080 plus 18x plus 10,368 rewritten as x to the negative 1. We have found the optimization function. That's the hardest part, in my opinion. Once you got that guy, don't you just differentiate and find out when it's 0, right? So let's work on doing that. Just rewrite it. 1,080, 18x, 10,368 x to negative 1. If you differentiate it, that's 0. That gets you 18, and multiply by the power and reduce the power by 1. And then do some style points on it. So the derivative of this function is that guy. So we're going to find its critical number, which is when its derivative is 0. So we are going to solve. Where is this ugly thing? 0. Technically speaking, shouldn't I also be looking for when the derivative is undefined? But there's a theme here. Won't this be undefined when x is 0? And won't x is 0 make the whole thing disappear? In other words, there isn't any picture or both. Yeah, there's nothing there, right? So we know that ain't going to happen. So that's the only one that we need to worry about. And since it is only one, we know it's the solution. Seen this before? Seen it a couple of times now. Would it do to both sides?
Yeah, 10,368 over x squared.
Yep. That's what experience does. See, if you see enough situations, don't you say after the third or fourth time, yeah, I've seen that before, this is what I did, right? That's how you kind of get used to these. Because the first time you're thinking, well, I'm not quite sure why he wants to do that. I might have done this or that instead. So if you do a cross multiply, you'll get 18x squared equals 10,368. Would you agree the next step would be to divide both sides by 18? So 10,368 divided by 18 is 576. Isn't that amazing that it's a nice answer? Which probably explains, as I said, why is that number there? That number's there probably because they wanted this to be nice. And then you take the square root, and the square root of 576 is 24. So if you want to build a big poster with a picture in the middle whose area must be 864, then you will make X this distance 24. And won't you make Y? Y is going to be, I've written it down somewhere. I did a piece of paper somewhere. Oh, it's that guy. Y is 864 over X, which is 864 divided by 24. And 864 divided by 24, and the answer I get is 36. Okay, and what do they want? Oh, they want the width of the poster and they want the height of the poster. Now, the width is not X and the height is not 36. Isn't that the width and the height of the picture in the middle? They want the poster, right? So if that's 24 from there to there, don't you add another 12 to either side? And that now becomes 24 plus the two pieces at the side. So 36 is the width. And the height is 36 plus two more nines, which is 18. And that gets you 54. Now, I'm glad I took a second look at that because I was about to just say, oh yeah, 24 by 36, we're done, right? But you can see actually, it was the poster, not the picture, right? So I guess the moral of that story is just be careful, right? Which I'm not as often as I should be. Any problems with that? We good? Okay. So let's continue then. I get time for at least one more. No, I'll keep that one till tomorrow. That's a really long one. Let's find a simple one to do. That way it won't take us so much time. So where are we? Question 5? Yeah, do question 5. The yield that you get out of a crop is Kn over 81 plus n squared. And N is the nitrogen level. And K is just a positive constant. So don't let the K bother you. Think K is 42, right? Whatever, a number. That's all a positive constant is. So in this question, we really don't need to do an optimization function. It's that guy. And we don't need to find out what K is in terms of N if you were worried about that. In fact, we are ready to move on to differentiate and find critical numbers. Now, if you want to differentiate this guy, would you agree that it's a quotient rule? Right, it's got n is the variable here, right? N in the top, n in the bottom. So it's going to be f dash g, take away f of g dashed, all over g squared. So if you differentiate, here's our first problem. N is the variable. What do you get if you differentiate k times n?
K
Yeah. Like 5n gets you 5, 10n gets you n, n. So, okay. Leave the other guy alone. Leave that guy alone and differentiate this guy. You get 2n. All over the bottom squared. Distribute, you get 81k plus k n squared. Take away 2k n squared. All over 81 plus n squared squared. So I just multiplied these together, multiplied these together. I'll try and collect some like terms now. That kills off one of those. And now you're looking at that. Style points. Is there anything you can do to the top line? Even if it's a minor thing, is there anything you can do to the top?
Factor out of k.
Mm-hmm. Do you recognize that 81 take away n squared is a difference of two squares and therefore can be factored? Right? 81 take away n squared can be factored. What are the two factors that you get?
9 plus n and 9 minus n.
Correct. Okay, so we are finished with style points. Haven't we factored the heck out of this, right? You can't factor it no more. It's done. So now we need to go looking for critical numbers, because the critical number is going to tell us the value of n that gives you the biggest yield, which is, I'm assuming, what the farmer would like, right? More crop per square foot, whatever. So we need to find critical numbers by finding out when the derivative is 0. And the guy that we've got might look quite ugly, and I guess it does look ugly, but it's not that difficult to solve. So here's my first thing. If I have a fraction equal to 0, I do not care really what the bottom is. It's not going to make the answer 0. So I've already managed to simplify it. Technically speaking, wouldn't one of the solutions be 9 and the other one comes out here, and that's -9. Do you see the benefit of factoring? Means finding those guys is easy. And then I'm going to kill one of the answers. I'm not going to use that one. Why is that one being kicked out of this story?
You can't have negative nitrogen levels.
Yeah, you can't make things have no more than 0. Right, 0 means you ain't get any, right? I can't imagine what -9 could ever mean. So in our world, the best nitrogen level to use would be n equals 9. Okay, so in a lot of ways, isn't this question easier because you already know the optimization function, right? You don't need to create it. On the other hand, would you agree the derivative was much uglier than many of the ones you've got? So hard to get optimization function, but easy to differentiate, or easy to get because they tell you, but really hard to differentiate. You see, there's you get one benefit and one kind of negative each situation. That's a perfect point for us to stop today. So